Right now, on the surface of your skin, a small and invisible exchange is taking place. Water molecules, warmed by the heat your body is quietly producing, are slipping away from your skin one by one and drifting into the air as vapor. You cannot feel most of it happening. It is too slow, too gentle, too small to notice, and that is exactly the point. If the room you are lying in is cool, some of that vapor might even be turning back the other way somewhere nearby, gathering as a thin film of moisture on a window, or settling as a faint dampness on a glass of water left on the nightstand. Liquid becoming gas. Gas becoming liquid. This has been happening to you, and around you, every second of your life, without asking for your attention, and without needing it. You do not have to understand any of this to fall asleep. You do not have to remember it either. There will be no test tomorrow, no diagram to fill in, no vocabulary word you'll be asked to define. Tonight is simply for listening, the way you might listen to rain on a roof without needing to know anything about where the rain came from. If your mind drifts, if you lose the thread for a while and come back to find yourself somewhere else in the description entirely, that is fine. That is, in fact, rather the idea. Let your attention be loose. Let it wander off and come back like a curtain moving in a slow breeze. What I want to talk about tonight is weather. Not any one storm, not any single forecast, but the whole slow, endlessly repeating churn of it, the thing that decides whether tomorrow will be humid or crisp, whether the sky will be the color of a nickel or scrubbed completely clean and blue. Weather can feel like a chaotic, unpredictable thing, and in some ways it is, but underneath the chaos there's something almost soothing once you see it. Weather is just heat and moisture, endlessly trying to even themselves out. That's really the whole story, at its core. Everything else is detail. Here is a way to picture it. Imagine you had a bathtub of water, and one end of the tub was heated while the other end stayed cool. You wouldn't need to do anything else. The water itself would begin to move. Warm water near the heated end would rise, because warm water is very slightly less dense than cool water, and it would drift along the surface toward the cooler end, sink there, and creep back along the bottom to be warmed again, round and round, without any pump, without any motor, driven by nothing but the difference in temperature between one end of the tub and the other. The atmosphere works the same way, only instead of a bathtub, it's a thin shell of air wrapped around an entire spinning planet, and instead of one heated end, it's the equator, baking under nearly direct sunlight, and the poles, tilted away and left comparatively cold. The sun does not warm the earth evenly. This is really the seed from which all weather grows. Near the equator, sunlight strikes the ground almost straight on, concentrated, intense, the way a flashlight makes a small, bright circle when you hold it directly above a table. Near the poles, that same sunlight arrives at a shallow, grazing angle, spread thin across a much wider area, the way that same flashlight, tilted nearly flat, casts a long, dim smear of light instead of a bright spot. Same sun, same amount of light leaving its source, but wildly different amounts of warmth actually delivered, depending on the angle at which it lands. This single geometric fact, that a sphere tilted at an angle receives sunlight unevenly, is the reason there is any weather at all. If the sun warmed every patch of earth exactly the same amount, the air would have no reason to move the way it does. It would simply sit there, more or less, at some uniform temperature, undisturbed. But the sun does not do that, so the air cannot simply sit there. The atmosphere behaves the way any fluid behaves when part of it is heated and part is not. It begins to circulate, trying in its slow and imperfect way, to smooth out the imbalance. Warm air near the equator rises, the way warm air rises above a candle flame, or above a radiator, or above the hood of a car that's been sitting in the sun. As it rises, it starts drifting toward the poles, cooling gradually as it goes, the way your breath cools as it leaves your mouth on a cold morning. Eventually, it sinks back down, and cooler air near the surface flows back toward the equator to replace the air that left. This movement of air, this endless attempt to distribute heat more evenly across the globe, is wind. It is really nothing more mysterious than that. Wind is air on its way somewhere, trying to fix an imbalance that will never quite be fixed, because the sun keeps creating a new one every single day. Moisture rides along on all of this. Water is unusual among the substances that make up our familiar world, in how easily it moves between its three states, solid, liquid, and gas, at temperatures we experience constantly in ordinary life. You have almost certainly, without thinking of it as remarkable, watched water do all three within a single afternoon: ice melting in a glass, a puddle disappearing from a sidewalk after a rain, your own breath turning briefly visible on a cold evening, a small cloud escaping your mouth and then vanishing again. Each of those is water changing state, absorbing or releasing a small quantity of heat as it does so, and each of those small events, multiplied by the size of an ocean or a continent or an entire atmosphere, becomes something we would call weather. The oceans matter enormously here, more than most people who haven't thought carefully about weather tend to assume. Water is very good at holding on to heat. It takes a long time to warm up and a long time to cool down again, compared to land or air. This means the ocean acts something like a great, slow battery for warmth, soaking up heat through the long days of summer and releasing it gradually through the winter, moderating the temperature of anything nearby. Sailors and coastal farmers understood this long before anyone had a word like thermal inertia to explain it. They simply knew that a house near the sea rarely froze as hard or baked as fiercely as a house 100 miles inland. The ocean was, without anyone fully articulating why, remembering the summer's warmth and lending it back out through the colder months. Evaporation off that ocean surface is where a great deal of weather truly begins its story. As the sun warms the sea, water molecules escape into the air above it as vapor, carrying with them a good deal of energy, the same kind of energy your own body loses when sweat evaporates from your skin on a hot day and leaves you feeling cooler. That vapor rises, invisible, into the atmosphere, and it does not stay invisible forever. Eventually, somewhere far from where it started, it will cool and gather and condense into the tiny droplets that make up clouds and possibly fall again as rain or snow or the fine gray mist that settles over a valley in early morning. Every raindrop that has ever touched your face was, at some earlier point, part of an ocean or a lake or a puddle or perhaps the damp exhale of a forest. So weather, at its heart, is this continuous project the atmosphere is always halfway through, moving heat from where there is too much of it to where there is too little, and carrying moisture along for the ride, lifting it, cooling it, letting it fall, and starting again. It never finishes, because the sun never stops shining unevenly on a spinning, tilted world, and the ocean never stops offering up its vapor into the waiting air. There is something almost restful in that, if you let yourself sit with it. Nothing about weather is random in the way that dice are random. It is closer to breathing, a vast, slow, planetary breath, in and out, warm rising here, cool sinking there, moisture lifted and released, over and over, longer than anyone has been alive to watch it. And it's that rising warm air, drifting away from the places where sunlight lands hardest, that we'll follow next, out past the equator and up into the layers of sky where the real shaping of weather quietly begins. Before we follow that warm air anywhere, it helps to just stand still for a moment and think about what up actually means when you are standing at the bottom of an ocean of air, because that is precisely where you are and where you have always been, whether you have thought of it that way or not. The air around you has weight. This sounds obvious once someone says it, and yet most of us go entire lifetimes without feeling it as true, the way we might not feel our own heartbeat until we press 2 fingers to our wrist and wait. A column of air stretching from the ground where you're lying all the way up to the edge of space presses down on you constantly, and on everything else, with a force that would surprise you if you could suddenly perceive it directly. At sea level, that column is pushing on every square inch of you with roughly 14.5 pounds of force. You don't notice, mostly because the air inside your own body pushes back with equal strength, the way a fish, deep in the sea, doesn't feel crushed by the water above it, because the water inside the fish is pressing outward just as hard. Balance, in both cases, is what allows for ease. It is only when that balance shifts, when you climb a mountain quickly or descend too fast in an airplane and feel your ears want to pop, that the pressure makes itself briefly, uncomfortably known. People took a long while to work this out, and the working out is a rather lovely piece of history to drift through. In 1643, an Italian scientist named Evangelista Torricelli filled a glass tube with mercury, sealed one end, and turned it upside down into a dish of more mercury, and noticed the mercury in the tube didn't all rush out. Instead, it settled at a certain height and stayed there, held up by nothing he could see. What he had actually built, without fully knowing it yet, was a scale for weighing air. The mercury stayed suspended because the air pressing down on the open dish was pushing back up through the tube with just enough force to hold that column in place. He had invented the barometer, and a few years later, a Frenchman named Florent Perrier, at the urging of his brother-in-law Blaise Pascal, carried one of these mercury tubes up a mountain called the Puy de Dôme, taking readings as he climbed, and found that the higher he went, the lower the mercury sat. There was less air above him to press down. He was, quite literally, climbing out from under some of the ocean of air that the people back in the valley were still submerged in. That single, patient experiment tells you something essential about the atmosphere, which is that it is not spread evenly like a blanket of uniform thickness. It is dense near the ground and grows thinner and thinner the higher you rise, the way a stack of pillows compresses more at the bottom than at the top, because the lower pillows are bearing the weight of everything above them. The molecules of air near sea level are crowded close together, jostled and squeezed by the sheer mass of atmosphere pressing down from above. Climb a few miles up, and those same molecules have room to spread out, drifting farther apart from one another, simply because there is less air stacked on top of them holding them close. This is density, and it thins out with altitude in a smooth, continuous way, no sharp edges anywhere, just a long, gentle fading, like a sound growing quieter and quieter the farther you walk from its source, never quite reaching silence until very far away indeed. Now, you might reasonably expect that air higher up, being closer to the sun, would be warmer, the way a room upstairs sometimes feels warmer than a room downstairs. But the atmosphere does not work this way, and it's one of those quietly confusing things worth sitting with slowly, rather than rushing past. The air near the ground gets most of its warmth not directly from sunlight passing through it, but from the ground itself, which absorbs sunlight and then radiates that heat back upward, warming the air closest to it first. The way a stone wall that has sat in the sun all afternoon will still be warm to the touch long after sunset, warming your hand more than the evening air around it does. As you move away from that heated ground, air temperature drops, roughly 3.5 degrees Fahrenheit, for every 1,000 feet you climb, until, several miles up, you would find the air distinctly, bitterly cold, cold enough to freeze exposed skin within minutes, even though you have moved that much closer to the sun itself. Distance from the sun, at these earthly scales, barely matters. What matters is distance from the warmed ground beneath you. This falling temperature is tangled up closely with the question of humidity, and it's worth understanding why, because it explains so much of what will follow. Warm air can hold far more water vapor, invisible and weightless seeming, than cold air can. Think of warm air as a much larger sponge than cold air, capable of soaking up and carrying far more moisture without releasing any of it. When that warm, moist air is lifted, by wind pushing it up a mountainside, or by simple buoyancy carrying it upward the way a hot air balloon rises, it cools as it climbs, and a cooling sponge is a shrinking sponge. It can no longer hold all the water it was carrying, so the vapor begins to condense, gathering itself into the almost impossibly small droplets, each one a fraction of the width of a human hair, that together make up what we call a cloud. This is why clouds so often form over mountains, over the leading edges of storms, anywhere air is being pushed or pulled upward. It isn't that moisture is being created out of nothing up there. It's that the air's capacity to hold what was already present quietly shrinks, and the excess has nowhere to go but into visible form. If you were to travel straight upward from where you're lying now, through this thinning, cooling air, you would pass through several distinct layers before leaving the atmosphere behind entirely, though the boundaries between them are gentle rather than sudden, more like the way dusk fades into night than like walls between rooms. The layer closest to the ground, called the troposphere, holds nearly all of the weather you have ever experienced, all the clouds and rain and wind and snow, and it reaches up only about 7 to 12 miles before giving way to the stratosphere, where the air turns strangely dry and calm, home to the layer of ozone that quietly absorbs a great deal of the sun's more punishing ultraviolet light. Above that lie the mesosphere and the thermosphere, colder and stranger and thinner still, until the atmosphere thins into something barely distinguishable from the vacuum of space at all. And here is a detail that tends to surprise people the first time they hear it. If the entire Earth were shrunk down to the size of an apple, the breathable atmosphere, the part that sustains every living thing you have ever known, would be thinner than the apple's skin. It is a remarkably delicate film, wrapped around an enormous stone, and everything we call weather happens within just the thinnest sliver of that film, close enough to the ground to still feel the day's warmth radiating up into the evening air. It's within that thin, lower layer, then, that the story continues, following the warm air as it lifts away from the sun-heated ground and begins its long, slow journey outward toward the cooler places that are waiting to receive it. Picture the sun in those first hours after dawn, still low against the horizon, its light arriving at a shallow slant rather than falling straight down. At that angle, the same beam of sunlight is spread out over a wider patch of ground than it will be at midday, its energy diluted the way a flashlight beam spreads into a soft oval when you tilt it against a wall instead of pointing it straight on. This is why early morning air still carries a chill even once the sky has brightened, and why the true warmth of the day tends to lag an hour or two behind the sun's highest point, arriving instead in the mid-afternoon, once the ground has had time to soak up the accumulating light and slowly give that heat back to the air above it. The ground and the water and the air itself all have their own particular patience about warming and cooling, their own thermal inertia, which is part of why the hottest part of the day so rarely lines up with the moment the sun sits directly overhead. That same slant of light, spread across a whole planet rather than a single morning, explains something much larger. Near the equator, the sun sits close to directly overhead for most of the year, its light striking the ground almost straight on, concentrated and strong. Travel toward either pole, and the angle grows shallower and shallower, the same amount of sunlight stretched across more and more ground, weaker and more diffuse, until in the deep polar winter, the sun may not clear the horizon at all for weeks at a stretch. The equator, then, runs warm nearly all the time, while the poles run cold nearly all the time, and everywhere in between sits somewhere along that long, gentle gradient. It's a simple geometric fact, really, nothing more mysterious than the shape of a sphere catching light from a single distant source, and yet from that one simple fact, nearly all of what we call climate eventually follows. The seasons layer a second rhythm on top of this. The earth doesn't sit perfectly upright as it circles the sun. It leans, tilted about 23.5 degrees off vertical, and it keeps that same tilt pointed toward the same fixed direction in space, all the way around its yearly orbit. For half the year, one hemisphere leans toward the sun, catching longer days and steeper, more direct light, while the other leans away, its days shortened and its sunlight arriving at a lower, weaker angle. 6 months later, the arrangement reverses. This is why summer in one hemisphere always means winter in the other, and why the changing seasons have so little to do, despite what people sometimes assume, with the earth moving closer to or farther from the sun over the course of a year. It's the tilt and the resulting angle of the light and the length of the day that matters, not the distance. So the sun heats the earth unevenly in at least 2 ways at once, by time of day and by latitude and season, and it's worth sitting with what that unevenness actually does to the air. Warm air is lighter than cold air, less dense, its molecules spread farther apart and moving more energetically, bumping into each other and pushing outward the way a crowd of people naturally spreads out when the room grows a little warmer and everyone loosens their coats. Because it's lighter, warm air tends to rise, the same way a hot air balloon rises once the burner has warmed the air trapped inside its envelope, buoyant against the cooler, denser air surrounding it. Cold air, by contrast, is heavier, and it sinks, settling low, the way a chilled draft pools near the floor of a room, even when the rest of the air feels comfortable. You may have felt this yourself standing near an open refrigerator, the cold air spilling out and washing over your feet before you've even had time to notice the ceiling above you hasn't changed temperature at all. When warm air rises off a patch of sun-heated ground, it leaves behind, ever so slightly, less air pressing down on that spot, what meteorologists call a region of lower pressure. Nearby, where the ground has stayed cooler and the air above it has stayed denser and heavier, the pressure presses down a little harder, a region of relatively higher pressure, and air, like water finding its way downhill, does not sit still in the presence of such a difference. It flows from where the pressure is higher to where it's lower, smoothing out the imbalance, the way water poured into one end of a tilted tray runs toward the low end until the surface levels out. This flow, this movement of air responding to a pressure difference, is wind in its most basic and essential form. Every breeze that has ever stirred a curtain or carried the smell of rain across a field began, in some fashion, as air answering an uneven distribution of warmth. On a small scale, you can watch a miniature version of this every day without realizing what you're seeing. Coastal towns often develop a reliable afternoon breeze blowing in off the water, because land warms up faster than the sea under the same sun, its surface heating and its air rising, drawing in cooler air from over the ocean to replace it. Come nightfall, the pattern often reverses, since land also cools faster than water once the sun goes down, and the breeze can shift to blow gently back out toward the sea. Sailors and fishing communities noticed this pattern long before anyone had a word like convection to explain it, learning simply that the wind could be trusted to shift with the hours of the day, as dependable as the tide. Now stretch that same idea across the whole planet, and you begin to see the outline of something much grander, the broad, slow circulation of the entire atmosphere. Warm air rises most persistently near the equator, where the heating is strongest and most constant, lifting skyward in a great, continuous column before spreading out toward the poles at high altitude, cooling gradually as it travels. Eventually, that cooled air sinks back down, not at the poles themselves, but at certain preferred latitudes along the way, before curling back along the surface toward the equator to replace the air that just left, completing a great looping cell of moving air. There is more than one such cell circling each hemisphere, nested one above another, and the pattern is complicated further, as you'll see shortly, by the fact that the Earth is turning beneath all this moving air the entire time. But the basic engine underneath it all is exactly what you'd expect from a planet heated unevenly by a single distant sun, rising air where it's warm, sinking air where it's cool, and a great deal of patient, ceaseless motion in between, carrying heat from the crowded, sunlit equator toward the colder, dimmer poles. An English astronomer named George Hadley worked out an early version of this picture back in 1735, sitting in London and puzzling over something sailors already knew from long experience, that steady winds seem to blow reliably from the northeast across much of the tropical Atlantic, winds so consistent that entire trade routes had been built around catching them. Hadley couldn't yet explain every detail correctly, but he grasped the essential shape of it, that heat rising near the equator and sinking again farther away was setting a great wheel of air turning, and that the wind sailors felt on their faces was simply that wheel passing by. It would take another century and a half, and a good deal more mathematics, before anyone understood why those winds arrived from the northeast rather than blowing in a straight line from north to south, as the simple picture of rising and sinking air alone might suggest. Let's set the wind aside for now, because that great looping wheel of air Hadley imagined is also, quietly, a machine for lifting water. And water, more than almost anything else in the sky, is what makes weather feel like weather to us, rather than just an abstract matter of pressure and temperature. So let's slow down and follow a single drop of water on its journey upward, because everything about clouds, and eventually rain, begins with a process so ordinary you've watched it 1,000 times without really seeing it. Take a puddle after a rainstorm. Over the course of a day, it shrinks, and then it's gone, and nobody carried it away in a bucket. What happened is that individual water molecules, jostling and colliding with each other the way molecules always do, occasionally picked up enough energy from that jostling to break free of the liquid altogether and drift off as invisible vapor into the air above. This is evaporation, and it's happening constantly, from puddles, from oceans, from the damp soil in a garden, from the surface of your own skin, from the wet leaves of a forest, breathing in the early morning. Warmth speeds it along, because warmer molecules move faster and collide harder, so more of them have enough energy to escape. That's why a wet towel dries faster on a warm day than a cold one, and why the ocean gives off far more vapor near the sunlit equator than it does near the icy poles. Now, air can hold this invisible vapor, but only up to a point, and that point depends heavily on temperature. Warm air can hold quite a lot of water vapor stretched out among its other molecules, rather the way a warm sponge has more room in it than a stiff, cold one. Cool air can hold much less. This single fact, that the capacity of air to hold water vapor rises and falls with temperature, is really the hinge on which almost the entire rest of this story turns, so it's worth letting it settle for a moment before we move on. Warm air, more room for vapor. Cool air, less room for vapor. Everything about dew, fog, and clouds follows from that one asymmetry. So imagine a parcel of air that's picked up a good deal of moisture, evaporated perhaps from a warm sea, and now imagine that air cooling down, the way air naturally does as it rises, or as evening falls and the ground loses its daytime heat. As it cools, its capacity to hold vapor shrinks. Eventually, it reaches a temperature where the air is holding as much moisture as it possibly can, right at the very edge of capacity. And that particular temperature has a name meteorologists have used for a long time: the dew point. It isn't a fixed number, the way freezing is always 0 degrees Celsius. It shifts around depending on how much moisture is actually in the air to begin with. A dry desert air mass and a humid tropical air mass will have completely different dew points, because one is starting with far less water to hold on to in the first place. Cool the air just past its dew point, even by a fraction of a degree, and it can no longer hold all the vapor it was carrying. Something has to give. And what gives is that the excess vapor stops being vapor at all. It condenses, turning back into liquid water, and this is precisely what happens on a summer evening when a cold glass of lemonade collects a fine, cool beading of moisture on its outside, or when the grass in the morning is silver and wet though it hasn't rained overnight. In both cases, nothing new arrived from outside. The water was already there in the air, invisible, and cooling simply forced it to become visible again. That's dew, and if the air near the ground cools past its dew point in a large enough layer rather than just against a cold glass, you get the same process spread out sideways instead of just condensing on a surface, which is what fog actually is. A cloud that has, in a sense, decided to sit down on the ground rather than float above it. Clouds higher in the sky form by the very same principle, just with the cooling happening for a different reason. Instead of the ground losing heat overnight, it's rising air cooling as it climbs, because air expands and cools the higher it goes, the same way air hisses out cold from a punctured bicycle tire. Somewhere above the ground, that rising air crosses its dew point, and the invisible vapor it's been carrying begins condensing, not on a blade of grass this time, but onto tiny floating particles of dust, sea salt, or pollen, specks so small you couldn't see one on its own, drifting everywhere in the atmosphere whether we notice them or not. Water gathers around these specks in droplets so minuscule, only a few thousandths of a millimeter across, that they hardly fall at all. They're light enough to be held aloft by the gentlest upward currents of air, the same way dust hangs suspended in a sunbeam. A cloud, really, is nothing more mysterious than an enormous crowd of these tiny droplets, drifting together, each one far too small and light to fall as rain on its own. Higher still, where the air grows cold enough, something else happens. Instead of condensing into liquid droplets, the water vapor may skip the liquid stage altogether and form directly into tiny ice crystals, a process with its own name, deposition, distinct from the simple freezing of already liquid water. These ice crystals tend to grow into six-sided shapes, because of the particular geometry of how water molecules lock together in a crystal lattice, and high, cold clouds, made mostly of these ice crystals, tend to look noticeably different from the low, warm clouds made of liquid droplets, wispy and combed rather than puffy and dense. And this brings us naturally to the different families of clouds themselves, because although they can look endlessly varied, meteorologists have long organized them by just two simple qualities: how high up they sit and what shape they take. In 1802, a London pharmacist and amateur meteorologist named Luke Howard proposed a classification system using Latin names, and it caught on so thoroughly that we still use his terms today. Picture, first, the low, flat clouds that sometimes stretch across the entire sky like a gray blanket, dimming the light without any real shape or texture to them at all. Those are stratus clouds, from the Latin for spreading out in layers, and they're the clouds responsible for those dull, uniform, overcast days that feel like the sky has simply run out of interest. Now picture something completely different: the tall, heaped, cauliflower-shaped clouds you might see on a warm summer afternoon, brilliant white on top where the sun catches them, with flat, darker bottoms, looking almost solid enough to climb on. Those are cumulus clouds, from the Latin for heap or pile, and they form when warm air rises in individual bubbling columns rather than spreading evenly, condensing as it climbs into these distinct sculptural towers. On a calm, fair day, cumulus clouds tend to be small and scattered, gentle punctuation marks against the blue. But given enough warmth and moisture to keep feeding them, the same cumulus cloud can keep growing upward, higher and higher, eventually swelling into something enormous and ominous, a cumulonimbus, the thunderstorm cloud, its top sometimes flattening out into a wide anvil shape where it hits a layer of air it cannot push through any further. And then, high above both of these, thin and feathery, and often catching a pink or gold light at sunset when the rest of the sky has already gone dim, there are the wispy ice crystal clouds called cirrus, from the Latin for a curl or a lock of hair, drifting so high and so cold that they're made almost entirely of those six-sided ice crystals rather than liquid droplets at all. Now, all of those clouds, whatever shape they happen to take, share a peculiar secret. The droplets and ice crystals they're made of are so small and so light that they don't actually fall. A typical cloud droplet is only about 1/100th of a millimeter across, smaller than the width of a human hair, and it floats there suspended, held up by air currents so gently rising beneath it that the droplet simply has nowhere to go. If you could somehow gather a whole cloud's worth of water into a single glass, you'd find there isn't nearly as much as the cloud's dramatic bulk might suggest, mostly just a great deal of very fine mist spread across a very large volume of sky. So the question worth turning over slowly, as the rain taps against a window somewhere tonight, is how anything ever gets heavy enough to fall out of something so delicate. Part of the answer involves something you'd never think to look for in a rain cloud: dust. Not visible dust, but the countless microscopic particles drifting invisibly through even the cleanest-looking air, tiny grains of sea salt flung up from ocean spray, specks of soil lifted by wind, flecks of soot, spores, even fragments of pollen. These particles are called condensation nuclei, and clouds could barely form without them. Water vapor, it turns out, is oddly reluctant to condense into a droplet all on its own in perfectly clean air. It needs something solid to gather around, some tiny surface to cling to, the way a bit of grit at the bottom of a soda bottle gives rising bubbles somewhere to start. Each cloud droplet, in other words, likely has a nearly invisible fleck of dust or salt at its very center, an accidental seed, arrived at completely by chance, around which the visible cloud eventually grows. For a droplet to become heavy enough to fall as rain, it has to grow enormously, roughly 1,000,000 times larger in volume than where it started, and there are two main ways this can happen. In warm tropical clouds, droplets grow mostly through collision, simply bumping into each other again and again as they jostle around inside the churning cloud, merging each time into something slightly bigger, until eventually the droplet is heavy enough that gravity wins out over the rising air holding it up, and down it comes. But in the colder clouds of higher latitudes, something more elegant tends to happen, something not fully worked out until the 1930s, when a Norwegian meteorologist named Tor Bergeron, building on an idea the German scientist Alfred Wegener had floated decades earlier, realized that ice and liquid water behave quite differently when they're crowded together in the same cold cloud. Ice crystals, it turns out, are greedier for water vapor than liquid droplets are, so in a cloud that contains both, sitting together at a temperature well below freezing, the ice crystals grow at the expense of the surrounding droplets, which slowly shrink and evaporate to feed them. The crystals swell rapidly this way, faster than droplets alone ever could, until they're heavy enough to fall from the cloud on their own. This quiet transfer of moisture from liquid to ice, now called the Bergeron process, is thought to be behind a great deal of the rain and snow that falls across the world's temperate regions, even in the middle of summer, which is a strange thing to picture, that plenty of a warm July rain may have begun its life a mile or two up as a snowflake. And that's really the heart of what makes precipitation so changeable on its way down, because what falls from the cloud and what actually lands on the ground can be two very different things, depending entirely on the air the falling water passes through. If the whole column of air between cloud and ground stays below freezing, an ice crystal simply continues falling as a crystal. And if conditions are just right, humid enough and cold enough, it keeps growing as it falls, other tiny ice crystals fusing onto it until it reaches the ground as a snowflake, each one built from the same basic six-sided symmetry, yet no two arranged in quite the same pattern, a detail the Vermont farmer Wilson Bentley spent decades in the late 1800s proving, through patient, freezing hours photographing snowflakes before they melted on his mittens. But if that falling snowflake passes through a layer of warmer air on its way down, even a fairly shallow one, it melts into an ordinary raindrop, and if it then drops back into a layer of freezing air closer to the ground, it can refreeze again before it lands, arriving as a small, hard pellet of ice that bounces slightly when it hits the pavement. That's sleet, and its existence really tells you something about the shape of the atmosphere that night, a kind of upside-down layer cake, cold near the cloud, a pocket of warmth in the middle, then cold again right at the surface. Freezing rain follows an almost identical path, with one crucial difference in timing. The snowflake melts in that same warm middle layer, but the cold layer near the ground is too thin or too shallow for the drop to freeze solid again before it lands, so it reaches the ground still liquid, still an ordinary raindrop in every way except that the ground itself, and every branch and wire and windshield it touches, is sitting right at or below freezing. The moment that liquid drop makes contact, it freezes almost instantly into a thin, often nearly invisible sheet of ice, which is exactly what makes freezing rain so quietly dangerous, since the road can look merely wet under a street lamp while actually being coated in glass. Hail takes a stranger route altogether, and it has almost nothing to do with winter. Hailstones form inside towering cumulonimbus thunderstorm clouds, the same violent, churning giants mentioned a moment ago, where powerful currents of rising air can be strong enough to fling a small ice pellet upward again and again instead of letting it fall. Each trip up through the cold heart of the storm adds another layer of ice, the way dipping a candle repeatedly in wax builds up its thickness, and each trip back down through the storm's wetter regions coats it in liquid before it's flung skyward once more. A hailstone only finally falls to earth once it's grown too heavy for even those powerful updrafts to hold it aloft, which is why cutting one open sometimes reveals rings, layer after layer, not unlike the growth rings of a tree, a rough record of how many times it rode that violent elevator before gravity finally settled the matter. Fog and dew, by comparison, are almost restful in how they form, since neither one requires any updraft or turbulence at all. Fog is simply a cloud that never bothered to lift off the ground, forming when air near the surface cools enough overnight for its water vapor to condense right there among the grass and rooftops, often in still, calm conditions, the same condensation nuclei doing their quiet work down at ground level instead of high in the sky. Dew forms through a related but slightly different process, needing no fog and no cloud whatsoever, just a clear, calm night in which the ground loses its heat quickly into open sky, cooling the blades of grass and the surface of a car below the temperature of the air just above them, until the moisture in that air condenses directly onto those cool surfaces, appearing, as if from nowhere, by the time morning comes. All of this, the rain and the snow, the sleet ticking against glass, the hail hammering a roof, the fog settling soft and silent over a valley, depends on temperature doing its quiet work along the way. And temperature, as it happens, is only half the story, because none of this water would be moving through the sky at all without something pushing the air itself, some invisible force nudging it from one place to another, which is where the story of wind quietly begins. Wind, at its simplest, is just air moving from where there's more of it pressing down to where there's less, the atmosphere's endless attempt to even itself out, the way water seeks its own level in a tilted pan. But air is restless in a way water rarely is, because the sun heats the earth unevenly, warming a sunlit field faster than a shaded forest, warming dark asphalt faster than a pale wheat field beside it, and every one of those small differences in temperature becomes a small difference in pressure, and every difference in pressure becomes, however briefly, a breeze. Consider the coast on a warm afternoon, since it offers one of the gentlest ways to watch this happen. Land heats up quickly under the sun, its solid surface absorbing warmth and passing it into the air just above it, while the sea beside it warms far more slowly, its enormous volume of water soaking up the same sunlight without much change in temperature at all. By early afternoon, the air over the land has grown noticeably warmer than the air over the water, and warm air, being lighter, rises, leaving behind a small patch of lower pressure right at the shoreline. Cooler, heavier air over the water flows in to take its place, and that flow, that quiet exchange of cool sea air sliding in beneath warm land air lifting away, is the sea breeze. The reason a beach in the afternoon so often carries a steady onshore wind even under a cloudless sky. Sailors, along coastlines from ancient Phoenicia to colonial New England, learned to time their departures around this rhythm long before anyone could explain why it happened, setting out in early morning calm and returning as the afternoon breeze filled their sails toward shore. Once the sun sets, the pattern quietly reverses. Land loses its heat quickly once the sunlight is gone, cooling faster than the sea, which continues to release the warmth it stored through the day. Now it's the air over the water that sits slightly warmer and lighter, and the air over the land that grows cool and heavy. so the breeze turns around and flows from land to sea instead, a land breeze, usually gentler than its daytime counterpart, drifting out over the water in the hours before dawn. The whole cycle, land warming and cooling faster than water, water warming and cooling more slowly, repeats itself every single day along every coastline on Earth, and quiet, patient breathing in and out that most people never consciously notice, even as it shapes the temperature of every evening walk along a pier. Mountains stage a similar drama, only turned on its side. During the day, sunlight strikes a mountain's slopes and warms the air resting against them, and that warmed air, lighter than the air at the same elevation over the open valley floor, rises up along the slope, drawing air up from the valley behind it to replace what's risen, a valley breeze flowing upward and toward the peak through the afternoon. At night, the story again reverses, the slopes cooling quickly once the sun is gone, chilling the air against them until it grows heavy and slides back down into the valley, pooling there the way water pools at the bottom of a basin, which is part of why mountain valleys so often turn surprisingly cold at night, even in summer. Cold air quietly draining downhill and settling wherever it can go no lower. These local breezes, born from nothing more than uneven heating over small distances, are the gentlest members of a much larger family. Scale the same basic idea up to the size of entire continents and oceans, and you begin to explain the great wind belts that circle the globe, the trade winds that once carried sailing ships steadily westward across the Atlantic, the prevailing westerlies that push weather systems across North America and Europe from west to east. But to understand why those winds blow in the particular directions they do, rather than simply flowing straight from warm regions to cold ones, it helps to sit with an idea that even careful thinkers have found genuinely strange the first time they meet it, something called the Coriolis effect. Here's one way to hold it gently in mind. Imagine standing at the very center of a large, slowly spinning carousel and rolling a ball in a straight line toward a friend standing near the outer edge. To you, watching from the middle, the ball leaves your hand traveling in a perfectly straight line, but your friend is moving, carried along by the carousel's rotation, and by the time the ball reaches the edge, your friend has swung around to a slightly different spot than where they were standing a moment ago. From your friend's point of view, standing on the spinning platform and feeling as though they themselves are perfectly still, the ball appears to have curved away from its straight path, bending gently to one side for no reason they can see. Nothing pushed the ball sideways. The ball never stopped traveling in its straight line. It's the platform itself, spinning beneath the ball's path, that made the straight line look curved to anyone standing on it. The earth is that carousel, and the atmosphere is the ball. Air setting out from one place to another over any real distance is traveling across a planet that is itself rotating underneath it, and so, to anyone standing on the surface and watching the wind's path, that air appears to bend, drifting to the right of its expected direction in the northern hemisphere and to the left in the southern hemisphere. This isn't some separate force reaching out and shoving the wind sideways, and it certainly isn't strong enough to determine which way water spins down a bathroom drain, a claim easily disproven by watching plenty of ordinary sinks and toilets swirl in whichever direction their particular plumbing happens to favor. The Coriolis effect matters at the much larger scale of storms and wind belts spanning hundreds or thousands of miles, patient enough to reveal itself only over those greater distances and longer stretches of time, gently steering the trade winds, curling hurricanes into their familiar spiral, and nudging the great rivers of high-altitude wind known as jet streams into their looping, wandering paths. Jet streams themselves are worth picturing carefully, since they sound almost mythical the first time you hear the name and are, in truth, just narrow ribbons of very fast-moving air, several miles up in the atmosphere, born from the same basic principle as every breeze already described, air responding to differences in temperature, except here the difference is between the cold air pooled near the poles and the warmer air lingering nearer the equator. Where these two air masses meet, high above the ground, the temperature contrast is sharp enough, and the Coriolis effect has had enough room to work its slow influence, that the resulting wind can reach speeds of over 100 miles an hour, a fast, narrow current threading its way around the planet, wandering north and south in long, lazy loops as the seasons shift the location of that temperature boundary. Airline pilots have long known to ride a favorable jet stream eastward across an ocean, the way a boat rides a strong current downstream, shaving hours off a flight, while battling the very same jet stream on the way back can add just as much time in the opposite direction. Yet none of this, not the sea breeze, not the mountain valley's nightly exhale, not even the jet stream roaring high overhead, unfolds over a perfectly smooth and featureless earth. The planet's actual surface keeps interrupting the wind's path at every scale, and it's worth slowing down to notice exactly how. The surface interrupts the wind constantly, yes, but before following that particular thread, it helps to pause on something the wind is always doing regardless of what lies beneath it, which is picking up the character of wherever it has been resting. Imagine a vast body of air, hundreds of miles across, sitting for days, or even weeks, over a single kind of landscape, the way a person might slowly take on the mood of a room they've been sitting in for a long while. Air parked over the snow and ice of northern Canada in winter grows cold and dry, borrowing those qualities from the frozen ground beneath it. Air resting over the warm tropical ocean near the Gulf of Mexico grows warm and heavy with moisture, soaking up humidity the way a sponge left in a puddle eventually takes on the dampness of everything around it. Meteorologists call these enormous, temporarily uniform bodies of air masses, and they name them according to where they were born and what they picked up there. Continental polar for the cold, dry air of the far north. Maritime tropical for the warm, wet air borne over southern seas. Each label a small biography of a parcel of air's recent history. Left alone, an air mass would simply sit and slowly change, warming or cooling to match whatever new ground lay beneath it. But air masses are rarely left alone. They drift, nudged along by the same pressure differences and Coriolis-guided currents already described, and sooner or later a mass of cold, dry air comes wandering into contact with a mass of warm, moist air. And here is where something interesting happens, because these two bodies of air, so different in temperature and density, do not simply blend together the way two glasses of water might when poured into the same pitcher. Air resists mixing far more stubbornly than water does. Instead, the two masses meet along a fairly narrow boundary, a few miles wide at most, and each stays largely intact on its own side of that boundary, at least for a while, the cold air staying cold and the warm air staying warm, like oil sitting on top of water rather than dissolving into it. That boundary is what gets called a front, and the name is not a coincidence. It was coined, quite deliberately, by a group of Norwegian meteorologists working in the city of Bergen during and just after the First World War. A father and son team, Wilhelm and Jacob Bjerknes, along with their colleagues, who were trying to make sense of exactly this kind of collision between air masses and reached for the vocabulary of the war then raging around them. To these scientists, the boundary between an advancing mass of cold air and a retreating mass of warm air looked something like the front line of a battle, one side gaining ground, the other falling back, and the name simply stuck, migrating from military dispatches into weather forecasts, where it has remained ever since, so thoroughly absorbed into ordinary speech that hardly anyone pauses any more to notice the metaphor sitting quietly inside it. There are, broadly, two kinds of these encounters, distinguished by which air mass is doing the advancing. When a mass of warm air is pushing forward into territory currently held by cooler air, the boundary is called a warm front, and because warm air is lighter than cold air, it does something rather graceful as it advances. It rises up and over the retreating cold air, sliding along its upper surface, much like a sheet of glass tilted gently upward, rather than shoving the cold air aside directly. This gentle, gradual climb means the warm air's moisture condenses slowly, high up at first, then lower and lower as the front approaches, which is why the classic warning sign of an approaching warm front is a thin, high veil of wispy cirrus clouds appearing on the horizon, sometimes a full day or two before any rain arrives, the sky's earliest possible notice that a change is coming. Those high, feathery clouds gradually thicken and lower over the following hours, cirrus giving way to a flatter, grayer sheet called altostratus, and that in turn thickening further into the low, featureless gray ceiling called nimbostratus, under which a steady, soaking rain typically settles in, not dramatic, not violent, just patient and persistent, sometimes lasting the better part of a day. And then, as the front finally passes overhead, the temperature climbs, the rain tapers off, and the warmer air mass that had been pushing from behind finally arrives to take up residence, often bringing with it a hazier, more humid kind of sky. A cold front behaves quite differently, because here it is the cold, dense air doing the advancing, and cold air does not slide gently up and over anything. It plows directly underneath the warmer air ahead of it, wedging beneath it the way a shovel might slide under a layer of snow and lift it abruptly upward. This is a faster, steeper kind of collision, and the warm air, forced suddenly skyward rather than rising gradually, tends to build tall, towering clouds rather than the flat gray sheets of a warm front, cumulonimbus clouds especially, the same dramatic anvil-topped giants capable of producing sudden, heavy downpours, gusty, shifting winds, and sometimes thunder and lightning, though usually for a much shorter stretch of time than a warm front's rain, often less than an hour before the sky clears rapidly behind it. That clearing is one of the more satisfying small dramas of everyday weather, the way a cold front can turn a muggy, hazy afternoon into a crisp, clean, blue-skied evening within the space of 30 or 40 minutes, the temperature noticeably dropping, the air suddenly feeling scrubbed and lighter, almost as though a window had been thrown open in a stuffy room. These fronts rarely travel alone or in a straight line. They are usually part of a larger, swirling system organized around a center of low pressure, the kind of sprawling, counterclockwise rotation in the northern hemisphere, already described when air spirals inward toward a region where the pressure is lower than its surroundings. Picture that low-pressure center as the pivot point of a slowly turning pinwheel, with a warm front extending out ahead of it on one side and a cold front trailing behind on another, the whole system creeping generally eastward across a continent over the course of several days, dragging its attached fronts along like the arms of that pinwheel sweeping through the sky. This is why a typical multi-day stretch of changeable weather so often follows a predictable script. First, the high, thin clouds of an approaching warm front, then the long gray soak of steady rain, then a mild and often muggy lull as the warm sector passes through, and finally the sharper, faster punch of the trailing cold front, with its brief, violent showers and its gusty wind shift, after which the air clears, cools, and dries, often quite beautifully, at least for a day or two before the next system, somewhere out over the ocean or the plains, begins its own slow approach. High-pressure systems, meanwhile, offer something like the opposite experience, because a high is simply a region where air is sinking rather than rising, spreading gently outward at the surface rather than converging inward. Sinking air does not favor cloud formation the way rising air does, since clouds are born from air cooling and its moisture condensing as it climbs, and sinking air does the reverse, warming slightly and holding on to its moisture as it descends. This is why a high-pressure system so often brings the kind of weather people describe simply as fine, clear skies, light winds, and a settled calm that can linger for days at a stretch, the atmosphere's version of a held breath, before the next low, with its trailing fronts and its familiar procession of clouds, arrives to stir things up all over again. The brief, violent showers that so often mark the passage of a cold front are usually the visible edge of something more interesting happening just above them, in towers of cloud that can rise higher than any mountain on the planet, and it's worth pausing here, gently, to look inside one of these towers and understand what a thunderstorm actually is, since so much about it seems mysterious until you see the simple physical story underneath. A thunderstorm begins, almost always, with air that is warm, moist, and unstable, meaning that once it starts rising, it keeps rising, cooling as it climbs, its water vapor condensing into cloud droplets that release a little heat of their own in the process, which in turn makes the air around them buoyant enough to keep climbing further still. This is the updraft, the rising column at a storm's core, and, in a strong thunderstorm, it can move at extraordinary speed, sometimes tens of meters a second, fast enough to keep hailstones suspended in the sky far longer than gravity alone would ever allow. As this updraft carries moisture higher and higher, the air eventually grows cold enough, even in the height of summer, for the cloud droplets to freeze, and somewhere between about -10 and -20 degrees Celsius, a particular kind of collision starts happening that turns out to matter enormously for everything that follows. Inside that frozen upper portion of the storm, two kinds of ice are colliding constantly. There are small, light ice crystals drifting almost weightlessly on the rising air, and there is a heavier kind of ice called graupel, soft little pellets formed when supercooled water droplets freeze onto a falling ice nucleus, something like a tiny frozen hailstone still finding its way through the cloud. When these graupel pellets fall through the crowd of rising ice crystals, they collide with them again and again, thousands of tiny collisions a minute, and in each collision, a small amount of electric charge transfers from one to the other. The physicists who worked this out in the early and middle 20th century, people like the Scottish physicist Charles Wilson, who spent decades studying atmospheric electricity, partly inspired by watching mist form on Scottish mountaintops, found that the direction of charge transfer depends on temperature and on how much liquid water is present. In the cold upper reaches of the storm, the lighter ice crystals tend to come away positively charged, while the heavier graupel comes away negative, and because the storm is, at its heart, a sorting machine, the light and positive crystals get carried up and out toward the anvil-shaped top of the cloud, while the heavier and negative graupel sinks toward the middle and lower levels, dragged down by both its weight and the storm's downdraft. The result is a cloud that has organized itself, without any plan, into something like an enormous battery, a broad region of negative charge low in the storm, and a broad region of positive charge high above it, with sometimes a smaller pocket of positive charge tucked in near the very base, close to where rain and hail are falling hardest. Underneath all this, down on the ground, The negative charge overhead induces a kind of mirror image, a spreading pool of positive charge that gathers at the surface and even climbs up anything tall and pointed, a tree, a steeple, a person standing in an open field, the way iron filings gather near a magnet. The charge difference between the base of the cloud and the ground beneath it can grow to be tens or even hundreds of millions of volts. An imbalance the atmosphere cannot simply tolerate forever, because air itself, ordinarily an excellent insulator, has its limits. Lightning is what happens when that limit is reached, an enormous spark that neutralizes the imbalance all at once, though the process is a little more layered than that word spark suggests. It typically begins with something called a stepped leader, a faint, forking channel of ionized air that creeps down from the cloud in short, nearly invisible jumps, a few dozen meters at a time, pausing for a fraction of a millisecond between each step as it feels out the easiest path downward, the way water finds the lowest route down a hillside. As this leader nears the ground, the strong positive charge waiting there sends up its own answering streamer, often from the tallest or sharpest object nearby, and when leader and streamer meet, they complete a conductive channel from cloud to earth. Along this newly finished path rushes the return stroke, the bright flash people actually see, a surge of current racing back up toward the cloud at a meaningful fraction of the speed of light, heating the air in its path to somewhere near 30,000 degrees Celsius, several times hotter than the surface of the sun, for a span of time so brief it's measured in millionths of a second. That sudden, violent heating is also the origin of thunder, since air expands almost explosively when heated that fast, shoving outward against the cooler air around it and creating a shock wave that settles, a short distance away, into the ordinary sound wave we hear as a rumble or a crack. The crack comes from the closest, most direct part of the lightning channel, while the longer rumble that follows is simply the same sound arriving from farther portions of that same jagged, miles-long path, each segment a little more distant and so arriving a little later, smeared out by the different lengths the sound has to travel and by the way it echoes off hills, clouds, and buildings along the way. Because light travels so much faster than sound, the gap between seeing a flash and hearing its thunder tells you, roughly, how far away the strike occurred, about 1 mile for every 5 seconds of delay, a rule sailors and farmers worked out empirically long before anyone understood what lightning actually was. Meanwhile, back inside the storm, that same relentless updraft is also responsible for hail, though hail requires a particular kind of patience from the storm, a willingness to keep an ice pellet aloft for far longer than gravity would prefer. A hailstone begins as a small frozen droplet caught in the updraft, and as it's carried up through layers of the cloud with varying amounts of supercooled water, it accumulates ice in coats, sometimes clear and glassy where it passed through especially wet, warmer air, and froze slowly, sometimes cloudy and opaque where it froze fast in drier, colder air, trapping tiny air bubbles as it did. If you were ever to cut a large hailstone in half, you would find these alternating layers laid out like the rings of a tree, a record of every trip the stone made up and down through the storm before it finally grew heavy enough, or the updraft finally weakened enough that gravity won out and it fell to the ground. It's worth noting, gently, that not every thunderstorm produces a tornado, and most don't, but the ones that do share a particular ingredient beyond simple instability, which is wind shear, meaning winds that change speed or direction with height. When this shear is strong enough, it can set a horizontal tube of spinning air rolling through the lower atmosphere, invisible until the storm's updraft tilts that spinning tube upright, stretching it vertically, the way a figure skater's spin quickens when the arms are pulled in. This vertical column of rotation, called a mesocyclone, can extend for miles inside the storm, and only in a small fraction of cases does it tighten and intensify further into the narrower, more violent funnel that reaches the ground as a tornado. Even then, the physics is really just an intensified version of the same rising and converging air already described in every low-pressure system, concentrated into a space measured in hundreds of meters instead of hundreds of kilometers, which is precisely why its winds, conserving that same angular momentum in such a tight space, can become so much faster and so much more forceful, not through any exotic new mechanism, but simply through scale. Severe weather, seen this way, isn't a departure from the ordinary rules already laid out across this description of the atmosphere, but rather those same rules: rising air, condensation, pressure differences, sorting by weight and temperature, all operating with unusual intensity in one compact place. It's a reminder that so much of the sky's power comes not from anything strange or hidden, but from perfectly familiar processes, given enough warmth, enough moisture, and enough room to build. Now let's widen the view again, away from the compact and violent, toward weather systems so large that you can only really see them from space, or from the patient accumulation of days and weeks on the ground. If a tornado is the atmosphere's power concentrated into a few hundred meters, a tropical cyclone is almost its opposite. The same basic ingredients spread across hundreds of kilometers, organized with a patience that takes days to build and days more to unwind. Where a tornado announces itself and vanishes within minutes, these larger systems move at something closer to the pace of a season, visible for a week or more on the same satellite loop, drifting like a slow bruise across an ocean basin. It begins, as so much of this story does, with warm water. Not just warm at the surface, but warm all the way down, typically above about 26 degrees Celsius through the upper 60 meters or so of ocean, because a storm this size needs a reservoir of heat deep enough that it can't simply stir itself cold in the first few hours of its own violence. A shallow patch of warm water is a poor foundation, easily churned up from below by the storm's own wind. Cool water dragged to the surface and the fuel supply cut off almost as soon as it's tapped. Warm water evaporates readily, and that evaporation is quietly loading the air above it with latent heat, the same stored energy from earlier in this description, waiting to be released the moment that moist air rises and its water vapor condenses back into cloud. Over the open ocean, especially in late summer when the water has had months to soak up warmth like a stone left all day in sunlight, clusters of ordinary thunderstorms can sometimes organize themselves around a shared center of low pressure, each storm's rising air feeding the next, each release of latent heat warming the column further and dropping the pressure a little more, drawing in yet more moist air from the surface in a widening spiral. Most such clusters never manage this. They flare up, rain themselves out, and dissolve within a day, ordinary and unremarkable. Only occasionally, when the surrounding winds are calm enough at different altitudes not to tear the young system apart, does the feedback take hold and begin to run on its own. This is the beginning of what meteorologists sometimes call a warm core low, a system that draws its strength not from clashing air masses, the way winter storms do, but from the simple, continuous exhaling of heat by a warm ocean into a cooling atmosphere above it. The spiral itself, that recognizable pinwheel shape seen in satellite photographs, comes from the same Coriolis deflection already described, air converging toward low pressure, but nudged sideways as it travels by the planet's rotation, curving instead of flowing straight in. That's also why these storms essentially never form very close to the equator, no matter how warm the water is there. because the Coriolis effect fades to nothing right at 0 degrees latitude, and without it, the spiraling motion that organizes a storm never gets started. A cluster of thunderstorms sitting directly over the warmest water on Earth, right along the equator, will simply pulse and rain and never quite manage to turn. As the system tightens, winds near the center accelerate, for the same reason a whirlpool speeds up as water spirals toward a drain, or the way a figure skater spins faster by pulling their arms in, angular momentum conserved as the radius shrinks, until at some threshold of sustained wind speed, the storm earns a new name. It is here that geography starts to matter more than physics, because this is fundamentally one phenomenon wearing different clothes depending on which ocean basin it forms in. In the Atlantic and the Eastern Pacific, it's called a hurricane, a word with roots in Caribbean and Central American languages for a storm god, absorbed into Spanish and then English by sailors who had no better word of their own for what they were encountering. In the Western Pacific, the same storm is called a typhoon, a word that may trace back to Chinese or Cantonese terms for a great wind, filtered through centuries of trade and translation along shipping routes that carried goods, language, and weather lore together. In the Indian Ocean and around Australia, it's simply called a cyclone, a more clinical term drawn from Greek roots meaning to coil or wind around, favored by the meteorologists who first mapped these storms' circular structure from ships' logs long before satellites existed. Different names, different alphabets even, but underneath them, the identical machine: warm ocean, rising moist air, latent heat, and a spiral organized by the turning of the Earth. At the center of a mature storm sits the eye, often startlingly calm, sometimes even sunlit, a small circle of blue sky ringed by towering cloud on every side, a detail that has surprised more than one ship's crew and more than one coastal resident throughout history into believing the storm had passed, when in fact only its first half had. Accounts from centuries of Caribbean and Pacific voyages describe exactly this mistake. Sailors venturing back onto open decks in the sudden stillness only to be caught, an hour or two later, by the second half of the eye wall, arriving with the wind now blowing from the opposite direction. The eye forms because air spiraling inward and rising in the surrounding eye wall, the ring of the storm's most violent wind and rain, can't simply keep converging all the way to the center. Some of it is flung outward by the same effects that spin an ice skater's arms out when the spin gets too fast, sinking gently in the middle, and sinking air, remember, warms as it compresses and clears of cloud. So the calmest place in one of the most violent storms on Earth turns out to be a direct consequence of the same rules governing high and low pressure everywhere else, just arranged into rings instead of the sprawling, loosely organized systems of mid-latitude weather. Once such a storm crosses onto land or drifts over cooler water, it's effectively cut off from the warm, moist fuel supply it depended on, and it begins to weaken, sometimes over a single day, its tight structure loosening and its winds slowing as the engine runs out of the specific heat it needs, the eye clouding over and filling in, the whole system gradually softening back into an ordinary area of rain and wind before it too dissolves. Related to this, though driven by a different rhythm, is the monsoon, a word that comes from an Arabic term for season, used for centuries by traders who learned to time their voyages across the Indian Ocean to the wind's reversal, sailing one direction for half the year and the opposite direction for the other half, their entire commercial calendar built around a pattern they could predict long before they understood why it happened. A monsoon isn't a single storm but a seasonal switch in wind direction across a whole region, driven by the uneven heating of land and ocean familiar from sea breezes earlier in this account, only stretched across a continent instead of a coastline, and across months instead of hours. In summer, a landmass like South Asia heats far faster than the surrounding ocean, its air rising and its surface pressure dropping, which draws in a steady inflow of moisture-laden ocean air that, forced upward over mountains and heated ground, releases months of accumulated rainfall in a single wet season, entire regions receiving most of a year's water in a stretch of weeks. In winter, the pattern reverses, the now cooler land holding higher pressure than the ocean, and the wind reverses with it, blowing dry air outward instead, leaving behind the long dry season that farmers and traders alike have planned around for generations. It's the same land and sea heating imbalance described near the beginning of this account of weather, simply operating on a scale so large and so slow that its full cycle takes an entire year to complete, rather than a single afternoon, the daily sea breeze stretched out until it becomes the rhythm of an entire calendar. Not all moisture arrives in an organized spiral or a seasonal reversal, though. Sometimes it arrives as a river, not of water flowing over ground, but of vapor flowing through the sky, a long, narrow corridor of concentrated moisture that can stretch for thousands of kilometers, often reaching from somewhere near the tropics all the way to a distant coastline, thin as a thread on a map of the whole hemisphere, yet carrying almost unimaginable quantities of water in invisible form. These atmospheric rivers, as they've come to be called only in recent decades of research, even though the phenomenon itself is ancient, can carry, at their peak, a volume of water vapor comparable to the flow of the Amazon River, funneled through a ribbon of air sometimes just a few hundred kilometers wide, a fact that still startles researchers who first began tracking these corridors with satellite instruments sensitive enough to see moisture the eye cannot. When such a corridor of moisture runs into a mountain range, the same forced ascent that wrings rain from any warm front does so here with unusual intensity and duration, because the river of moisture keeps flowing, keeps rising, keeps condensing, sometimes for days on end without pause, the mountains acting like a wall that the sky simply cannot get over without leaving something behind. This is how a single storm system can leave a place drenched in what feels like months of rain compressed into a week, hillsides saturated past their limit, rivers rising far faster than the calendar would suggest they should, and it's also, on the coasts that depend on this seasonal moisture, how a significant share of an entire year's water supply can arrive in just a handful of these events, reservoirs filled and snowpack built in a handful of storms, rather than a steady winter's accumulation. It's a reminder that even something framed dramatically as extreme is often simply an essential process operating at its upper reach rather than its comfortable middle, the same gentle physics of evaporation and condensation, only turned up until it becomes newsworthy. Winter offers its own version of concentrated moisture, arriving not as rain, but sculpted into individual crystals, each one, as noted earlier, unique in its fine structure, yet obeying the same six-sided symmetry every time. The people who first tried to understand what tomorrow's sky might hold had none of this vocabulary, no fronts or systems or crystalline geometry, only their own accumulated noticing, passed down as rhyme and proverb, because rhyme is what survives when writing is scarce. Red sky at night, sailors delight. Red sky in morning, sailors take warning. A couplet that sounds like folk charm, but that actually encodes something real about how sunlight scatters through moisture-laden air approaching from the west, where most weather in the temperate latitudes tends to travel from. A ring around the moon meant rain was coming, and it often did, because that ring is caused by ice crystals in the thin cirrus clouds that frequently arrive a day or so ahead of a warm front, the same gentle overrunning described earlier in this account, visible to anyone patient enough to look up and remember what happened the last time they saw it. Farmers watched how low swallows flew, since insects drop closer to the ground when humidity rises and air pressure falls, and the birds, hunting the insects, dropped with them. None of this required instruments. It required only generations of people staying in one place long enough to notice patterns and pass the noticing forward, an oral weather service built entirely out of attention. The first attempt to move beyond folk pattern into something more like a physical account of the sky came from Aristotle, who in the 4th century before the Common Era wrote a treatise called, in translation, simply Meteorology, from a Greek word for things suspended in the air. Aristotle's explanations were often wrong in their particulars. He thought wind arose from a kind of exhalation of the earth, but the ambition of the work mattered more than its accuracy, because it treated the sky as something that could be reasoned about rather than only endured. For nearly 2,000 years afterward, that treatise remained the closest thing the Western world had to a scientific account of weather, which says less about the quality of the answer than about how long it took anyone to ask the question again with fresh tools. Those fresh tools arrived, when they finally did, not from astronomers or philosophers, but from people building instruments for other purposes entirely. In 1643, an Italian named Evangelista Torricelli, a student of Galileo, was investigating why water pumps could not lift water more than about 10 meters, a practical mining problem, when he filled a long glass tube with mercury, inverted it into a dish of the same liquid, and watched the mercury settle at a height and leave an apparent void above it. That column of mercury, rising and falling slightly from day to day, turned out to be responding to the weight of the air pressing down on the open dish, and Torricelli had, almost incidentally, built the first barometer, the first instrument capable of measuring something about the atmosphere that no human sense could feel directly. Around the same period, thermometers were being refined by several hands across Europe, eventually standardized in the early 18th century by Daniel Fahrenheit, who used mercury sealed in glass and calibrated his scale against a mixture of ice, water, and salt at one end, and, by some accounts, the temperature of the human body at the other. For the first time, two people in two different cities could compare what the air was actually doing rather than only what it felt like. And comparison, it turns out, is the seed from which every later forecast eventually grew. Still, an instrument reading in one place tells you only about that place at that moment. What changed everything, or at least made anything resembling a genuine forecast possible, was the ability to gather many such readings from many places at once and see them together, and that required a technology that had nothing to do with weather at all, the electric telegraph. Once telegraph lines spread across Europe and North America in the mid-1800s, it became possible for the first time in human history to know, within hours rather than days, what the weather had been doing somewhere far upwind. And since storm systems generally travel from west to east across the temperate latitudes, knowing what was happening upwind was almost the same as knowing what was coming. Robert Fitzroy, who had once captained the ship that carried Charles Darwin around the world, became in the 1860s the head of what was essentially the first government weather service in Britain, using telegraphed observations to issue storm warnings to coastal towns. And though his early forecasts were mocked in the press for their frequent errors, the underlying idea that scattered observations gathered quickly enough could reveal a pattern moving through space was sound, and it never really went out of use again. For decades after that, though, all of this observing happened close to the ground, because there was no practical way to sample the atmosphere at altitude, and altitude, as this account has described in the discussion of fronts and jet streams, turns out to matter enormously. That gap began closing in the early 20th century with the weather balloon, a simple enough idea, a hydrogen or helium-filled envelope carrying a small package of instruments upward through the layers of the atmosphere while radioing back readings of temperature, humidity, and pressure as it rose. These instrument packages, called radiosondes, still go up twice a day from hundreds of sites around the world, launched by hand at the same two moments, dawn and early evening, in a shared reference time, so that the atmosphere over the whole planet can be sampled simultaneously, a coordinated ritual that has gone on quietly, twice daily, for nearly a century. Radar arrived by accident, or more precisely as leftover technology from a different purpose entirely. Developed during the Second World War to detect approaching aircraft, radar operators soon noticed that their screens were sometimes cluttered with echoes that had nothing to do with airplanes, blooms, and streaks that turned out to be rain, showing that the same pulses of radio energy bouncing off metal could bounce off droplets of water suspended in a storm. After the war, meteorologists adapted the technology deliberately, and by pointing radar dishes not at the sky in general, but tracking the intensity and movement of precipitation, they gained the ability to watch a storm's structure evolve in something close to real time, seeing the very shape of a supercell's hook, the leading edge of a squall line, in a way that no ground observer looking up could ever have managed. Then, in 1960, came a view that no one on Earth had ever had before at all. TIROS-1, a satellite roughly the size of a large drum, was launched into orbit carrying television cameras, and within days it returned the first photographs of Earth's cloud systems taken from space, revealing entire storm systems as coherent spirals, whole weather patterns visible whole in a single frame instead of pieced together from scattered ground reports. It is easy, looking at a satellite loop today, to forget how recent and how strange this capability once was. For all of human history before that, no one had ever seen a hurricane's shape, only felt its wind and rain from within one small part of it. Suddenly the shape itself was visible, and understanding followed the seeing. The atmosphere is not the whole story, though, because so much of what happens in the sky is driven by what the ocean beneath it is doing, its warmth or its chill, its slow release or absorption of heat over months and years. Sampling that ocean systematically required its own network, and beginning in the later decades of the 20th century, arrays of moored and drifting buoys were scattered across the tropical Pacific and elsewhere, anchored instruments bobbing quietly for years at a time, patiently recording sea surface temperature and feeding it back by satellite link, data that turned out to be essential for anticipating events like El Niño long before their effects reached any coastline. All of these instruments, balloons and radar and satellites and buoys, produce staggering quantities of numbers, and numbers alone are not a forecast. Turning them into one required treating the atmosphere as a physical system whose future state could, in principle, be calculated from its present state using the equations of fluid motion, an idea proposed in the early 20th century but genuinely attempted only after electronic computers existed to do the arithmetic. In 1950, a small team working with one of the first electronic computers, a machine called ENIAC, ran what is generally considered the first successful numerical weather forecast, a calculation that took about 24 hours of computer time to predict 24 hours of weather, a pace that made the achievement scientifically thrilling and practically useless in the same breath, since the forecast finished no sooner than the weather it described. It would take decades more of faster computers and better equations before numerical prediction could outrun the sky it was trying to describe. Once computers finally could outrun the weather, it seemed only a matter of time before forecasts would simply keep getting better, year after year, until the sky held no more surprises. And in a sense that has happened. Forecasts today are remarkably more accurate than they were even a few decades ago. But somewhere in the middle of the 20th century, a discovery emerged that quietly set a boundary on how far that improvement could ever go. And the discovery came, fittingly, from a man who was not trying to find it at all. Edward Lorenz was a meteorologist at the Massachusetts Institute of Technology in the early 1960s, running a simple computer model of the atmosphere, just a handful of equations meant to mimic the churn of rising and sinking air. One day he wanted to rerun a particular sequence a little longer, so rather than starting the whole calculation over from the beginning, he took a printout of numbers from partway through an earlier run and typed them back in as a new starting point, expecting the machine to simply continue where it had left off. Instead, the new run diverged from the old one almost immediately, and within what represented a couple of simulated months, the two versions of his toy atmosphere looked nothing alike. He eventually realized the cause was almost embarrassingly small. The computer internally stored numbers to 6 decimal places, but the printout he had retyped only showed 3, and he had entered those rounded values without a second thought, assuming a difference of 1 part in 1,000 couldn't possibly matter. It mattered enormously. That tiny rounding error, smaller than the width of a human hair set against the size of a room, had grown, doubling and doubling again, until it swallowed the entire forecast. This sensitivity to starting conditions is often called, a little too casually, the butterfly effect, after a phrase Lorenz used years later in a talk asking whether the flap of a butterfly's wings in Brazil could set off a tornado in Texas. He wasn't claiming that it literally does, and it's worth resisting the urge to picture some grand chain of cause and effect stretching from one wing beat to one storm. The deeper point is quieter and stranger than that. In a system like the atmosphere, made of countless interacting parts all pushing and pulling on each other, it is not possible, even in principle, to know the present state with perfect precision, and any imperfection in that knowledge, no matter how minuscule, grows over time until it overwhelms your ability to say what comes next. This is chaos in the scientific sense, and it is worth pausing on how different that is from what people usually mean by the word in ordinary conversation. Chaos does not mean randomness. A coin flip is random, in the sense that no amount of additional information about the coin would let you predict which way it lands, at least not without measuring its spin and launch with an impossible degree of precision. But a chaotic system like the atmosphere is not random at all. It follows exact physical laws, the same laws every time, with no dice being rolled anywhere inside it. Given a starting condition, its future is, in principle, completely determined. The trouble is only that we can never know the starting condition with enough precision, and the system's own internal dynamics amplify that unavoidable uncertainty faster than we can measure it away. It's a bit like a marble balanced on the ridge of a steep hill. Nudge it a hair to the left and it rolls down one slope, a hair to the right and it rolls down the entirely different slope on the other side, and the outcome is completely determined by physics at every instant, yet wildly sensitive to a starting nudge too small for you to ever fully control. That is chaos, order, and unpredictability tangled together, not the absence of order, but a particular, delicate kind of order that punishes even the smallest ignorance. This is why weather forecasts fade in reliability the further out they reach, not because forecasters are careless or their models are crude, but because the atmosphere itself imposes a kind of horizon on prediction, a point beyond which no amount of additional computing power or additional weather balloons could push back very far, since the errors that matter start smaller than any instrument can measure. Modern forecasting has adapted to this limit rather than pretending it doesn't exist, running many slightly varied versions of the same forecast, starting from slightly different initial conditions, an approach called ensemble forecasting, and then looking at how much those versions agree or disagree with one another. When they mostly agree, confidence is high. When they scatter widely, that scattering is itself useful information, an honest signal that this particular stretch of sky, on this particular day, is simply less knowable than usual. Given all this uncertainty about next Tuesday's weather, it might seem strange that scientists can speak with much more confidence about the climate decades from now, and this puzzle deserves a careful answer, because weather and climate are not the same kind of question, even though they concern the same atmosphere. Weather is the specific, individual state of the sky at a particular place and moment, the chaotic marble balanced on its ridge. Climate is something else. It is the statistics of weather over long stretches of time, the shape of the distribution from which all those individual chaotic days are drawn. You cannot predict which number will come up on a single roll of a die, but you can say with complete confidence that if you roll it many thousands of times, roughly 1/6 of the rolls will show each face, because that confidence rests on the properties of the die itself rather than on tracking any individual roll. Climate works something like that. No one can tell you whether it will rain in a particular city on a particular afternoon 5 years from now, but the underlying conditions that shape the odds of rain, the average temperatures, the patterns of pressure and moisture that set the background against which each day's chaos plays out, those can be understood and, within limits, projected forward, because they depend less on the impossible precision of a single starting condition and more on slower, steadier forces like the amount of energy accumulating in the ocean and atmosphere over time. And this brings up something important, which is that the background conditions themselves are not fixed. They drift, sometimes slowly across centuries and sometimes more quickly, and when they shift, the whole distribution of possible weather shifts along with them, even though any single day still remains as chaotic and individually unpredictable as ever. Picture that die again, but imagine its faces are not evenly weighted. Imagine someone has very slightly shaved down one corner so that it lands on 6 just a bit more often than it used to. You would still be unable to predict any single roll. But the odds themselves would have moved, and if you rolled it enough times, you would eventually notice more 6s than before, especially at the extreme end, more 6s in a row than the old die had ever produced. This is roughly how a warming background climate interacts with extreme weather. It does not manufacture any particular storm or heat wave out of nothing. The atmosphere was always capable of producing hot days and heavy rain even without any long-term warming at all. What shifts is the frequency and the intensity clustered at the far edge of what is possible, the tail of the distribution stretching further than it used to, so that events which were once rare become somewhat less rare, and the ceiling on how extreme a heat wave or a downpour can be creeps a little higher than it once stood. Untangling how much of any single event owes to that shifted background, and how much belongs to the ordinary chaos the atmosphere has always contained, turned out to require its own careful branch of science, one that emerged only once meteorologists had grown comfortable asking not just what the weather would do, but what it would have done in a world shaped slightly differently. Which brings us, gently, to a kind of closing thought, the sort you might have while lying still and letting your eyes finally lose interest in staying open. All of this, the fronts and the pressure systems, the clouds built from nothing but rising damp air, the storms that spin because the earth itself is spinning, the seasons that arrive because a modest tilt points one hemisphere toward the sun and then, months later, points it away. All of this is really one system. Not many separate things happening to coexist on the same planet, but one continuous exchange, endlessly trading energy back and forth between four great partners: the ocean, the land, the sunlight, and the air above them. Consider how quietly the ocean has been doing its work this whole time, even while we were talking about clouds and fronts and pressure. Water covers most of this planet, and water is a peculiar substance in a way that turns out to matter enormously for weather. It takes a great deal of energy to warm water even a little, far more than it takes to warm the same mass of rock or soil or air by the same amount. This is why a paved parking lot can feel like a griddle by early afternoon, while the ocean beside it has barely warmed at all, and it is why that same ocean, having absorbed the sun's heat slowly all day, releases it slowly too, keeping coastal nights gentler than desert nights far inland. The ocean, in other words, behaves like a colossal thermal flywheel, soaking up energy when there is a surplus and giving it back when there is a deficit, smoothing out what would otherwise be far more violent swings between day and night, between summer and winter. Without that reservoir of water absorbing and releasing heat on its own unhurried schedule, the temperature swings on this planet would be sharper, faster, far less forgiving. And the land plays its own part, though a different one. Where the ocean stores heat and releases it slowly, land does almost the opposite. It heats quickly under direct sun and cools quickly once the sun sets, which is part of why deserts can scorch by day and turn bitterly cold by night, with none of the ocean's patience to soften the transition. This difference in how ocean and land handle the same sunlight is not a minor detail. It is one of the central engines driving air movement across the whole planet. Air over land heats and rises faster than air over nearby water, creating small pressure differences that pull cooler ocean air inland, which is the same afternoon sea breeze you might have felt on a beach without ever wondering what caused it. Multiply that same idea across an entire continent and an entire season, and you get monsoons, the great seasonal winds that reverse direction as land and ocean trade places in which one is warmer, drawing moisture inland for months, and then releasing it again as rain that entire civilizations have depended on for their harvests. Underneath both of these, quietly funding the whole operation, is sunlight, though even that phrase undersells how unevenly this funding gets distributed. The sun does not warm the earth evenly, not because the sun favors any particular place, but because the earth is curved and tilted, so that sunlight strikes the tropics almost directly overhead, while it strikes the poles at a long, glancing angle, spread thin across more surface for the same amount of energy. This uneven warming is really the root cause of nearly everything we have discussed. It is why warm air rises at the equator and eventually sinks back down in the subtropics, creating the belt of deserts that circle the globe at those latitudes, not because those places are unlucky, but because that is simply where descending, drying air tends to land. It is why the jet stream exists at all, a fast-moving river of upper air, formed at the boundary where warm tropical air meets cold polar air, a boundary that is never perfectly still, because the temperature difference feeding it is never perfectly stable. Nearly every large weather pattern you could name traces back, if you follow the thread far enough, to this same uneven heating and the atmosphere's ceaseless, imperfect attempt to even it out. And this is really the simplest way to think about weather as a whole, stripped of its individual storms and fronts and cloud formations. The atmosphere and ocean together form a vast redistribution system, constantly moving heat from where there is too much of it toward where there is too little, from the equator toward the poles, from ocean to land and back again, from day to night. Every wind you have ever felt, every rain cloud, every hurricane, and every gentle afternoon breeze is in some sense a piece of that same redistribution, energy in transit, taking one particular form or another, depending on where it happens to be moving and how much of it there is to move. Storms are not malfunctions in this system, they are the system working, sometimes working with more drama than we would prefer, but working according to the same simple physical rules that also produce the mildest, most unremarkable afternoon. There is something almost soothing in seeing it this way, if you let yourself sit with it for a moment. The complexity we have spent all this time working through, the fronts, the pressure gradients, the chaos underlying prediction, the subtle shifting of long-term odds, none of it is separate from the ordinary rhythms of your own day. When you feel the temperature drop before a summer storm, you are feeling cold air pushing beneath warm, exactly as we described. When you notice the sky redden at sunset, you are watching the same scattering of light that explains why the sky is blue at noon, just viewed through a longer, dustier slice of atmosphere. When you step outside after rain and catch that particular mineral scent rising from warm pavement, you are noticing oils and bacterial compounds released by the same process meteorologists have a name for, though the name matters far less than the noticing. None of these things require you to remember a single term from tonight. They only ask that you keep being, as you already are, a person who occasionally looks up. And now, if you are still here, still listening, notice your own breathing for a moment. Notice how it rises and falls without your directing it. Air moving in and out of you the same way air moves across the whole planet, quietly, continuously, without asking your permission or waiting for your attention. Your chest rises, gently, the way warm air rises from sun-warmed ground. It falls again, gently, the way cool evening air settles back toward the earth once the sun has gone. There is no pressure gradient you need to calculate, no front you need to track, nothing tonight that requires your attention at all. The weather will keep happening exactly as it always has, whether you are awake to notice it or not. Oceans slowly trading their stored warmth with the air above them, land cooling under a sky it cannot see, wind quietly moving heat toward wherever it happens to be needed most. You do not have to keep any of it running. You never did. You can simply let your breathing slow, let your shoulders soften into whatever is holding you, and let the vast, patient, endlessly cycling system of this planet continue its work without you, the way it always has, long before you were listening and long after you have drifted off. Rest well.